so if we just look at some example questions that you might get for organic chemistry. This first one says that we have many organic compounds, including alcohols, carbonyls, carboxylic acids, esters, and they'll contain oxygen. And then they're giving you a table below that lists some oxygen-containing organic compounds and some common lab reagents. Now you need to complete the table. If you think no reaction occurs, you can write no reaction in the box as well. And we need to draw the structural formula of the products. So we've got all these organic compounds and the reagents that they're mixing with, and we need to know what's going to happen in the end. So the first thing we need to do is identify what are our functional groups in each of these compounds. So this first one, since it's drawn in structural formula, we can draw it out so we can see what we're dealing with. We have CH3, and there's 3 of them attached to a carbon. So I've got carbon, and that's a CH3, a CH3, and a CH3 on it. And then that carbon is also attached to an OH. So we can see we've got an alcohol. Our next one, we have a CH3, a CH2, followed by a CHO. And we know that CHO means aldehyde at the end. Then I've got a C with an H on it, and then I've got O2, and then another C. So it means that there's an O and an O, but in order for carbon to have all of its bonds, it means that must be double. And then that is then attached to a C, H, and then CH3, 2. So there's 2 CH3 groups on this carbon. So I've got a CH3 and a CH3. So I can look at that and I can see that is then an ester because I've got the O in the middle with that. Then I've got CH2 double bonded to CH, and then another CHO. So that next C must be another aldehyde. Then I've got CH3, CH3, 3 on that C. So that's the same as our first one. So I've got carbon with 3 CH3 groups attached to an OH. And then my last one, I have got a CH3, CH2, C, O, and then a CH3. So this C is attached to an O and a CH3. But that means this O must be double bonded for carbon to have its 4 bonds. So that means I have a ketone because I've got double bonded O on the carbon with 2 carbons on either side. So now I know what my functional groups are. Now I can see, are they going to react in the end? So our first one was the alcohol, and its reagent is with dichromate with H+, and whenever you see H+, it means acid. So I've got acidified dichromate with heat under reflux. So since I'm dealing with an alcohol, I can have a look at my reactions, and I know that a dichromate is an oxidizing agent. So if it's an oxidizing agent, it means it's going to create more double bonds. Okay? But if I look specifically at this OH, that carbon is attached to 1, 2, 3 carbons. There is no H bonds around there to join for this oxygen. So because there's no extra bonds, it makes this a tertiary alcohol, and tertiary alcohols cannot be further oxidized. So my first one, I say no reaction in there. So now I'm done with my first one. Then I look at my second one. Now my second one I identified was the aldehyde. That says it's reacted with Fehling's reagent that's warmed up. And I know that Fehling's reagent is what we use to identify aldehydes because they have an oxidation reaction with the Fehlings that contains copper, because this can be further oxidized. So if this is double bonded O, only this bond can be further oxidized, and in order to further oxidize it, I can add an O with the H to turn this aldehyde into a carboxylic acid. So now I can write my carboxylic acid at the end, but it's said specifically in structural formula. So structural formula means I've got CH3, then I've got CH2, and then I've got CO2H because I've got my carboxylic acid. Then my next one, I identified it as an ester. So now it's reacted with sodium hydroxide and warmed up. And I know that sodium hydroxide can reverse my ester reaction. So when I want to reverse it, because before, to make the ester, I take an alcohol plus a carboxylic acid and I join them with an acid catalyst. Now I'm taking a hydroxide, so I am going to split my ester where my ester bond is, and the alcohol side goes back to being an alcohol. So I've got my compound here that is going to take my OH back. And on the carboxylic acid side, when a carboxylic acid is reacted with sodium, we can form our F oxide. So this carboxylic acid is going to keep its carbon and its hydrogen and its oxygens, because there was 2 of them, and that oxygen there is going to join with the sodium, as well as I have my CH3, CH2OH now, and then CH3. So I can write that structurally. I've got the CH3, the CH2, which has the OH because I went back to the alcohol, CH3. So now my next one, it says I've got my double bond as well as an aldehyde in both of them, and we reacted it with NaBH4. And NaBH4, we know, is a reducing agent. So if there's any oxygens in here, they can be reduced. And there is, because there's an aldehyde group. The double bond doesn't have any oxygen, so it's going to stay exactly as it is. But this side can be reduced. And if I take a carboxylic acid and reduce it, it means I take away my double bond and I turn it into an alcohol group. So in the end, I can write my double bond as it is. So I've got my CH2 double bonded to my CH. But now this carbon over here goes from an aldehyde to an alcohol. So it becomes CH2OH. Then I've got my tertiary alcohol again, and it's with NaBH4, which is the reducing agent. But now it's already an alcohol, so it's already reduced as much as it can go. So that means it cannot be reduced anymore, so we say no reaction. And then the last one was the ketone, and a ketone with MnO4/H+, meaning it's acidified potassium manganate with heat under reflux. So manganate that's acidified is an oxidizing agent. So it means we want to add more oxygens, but this is a ketone. So it's already as oxidized as it's going to go. Can't be oxidized any further, so we also say no reaction. So that's the kinds of questions that we're going to look at. If we move on to the next one from there, it says during some of the reactions on the previous question, color changes occur. And you need to complete the table below for any such reactions, stating the letter of the reaction and the color change. So, if we look at what we had, our dichromate has a color of orange, but that had no reaction, so that can't be there. The Felix reagent we know has a color, and it starts off blue, and if it reacts with an aldehyde, it goes reddish orange, and it did react, so that's one we can write. So that was reaction B. So we can write that we had reaction B. The color at the beginning is blue, and the color at the end is an orange-red. Then sodium hydroxide doesn't have a color, neither do our reducing agents of sodium borate tetrahydrate. And then manganate does have a color because it's purple, but here there was no reaction. So the only one of these that actually had a color change was B. And that's the only thing we need to fill in there. So then the next question says, some oxygen-containing compounds react with 2,4-dinitrophenylhydrazine, and they give you what that compound looks like. And it says you need to draw the structural formula of the organic compound formed when this compound reacts with 2,4-dinitrophenylhydrazine. So if we look at this compound, that side, the OH, is an alcohol group, and that side is an aldehyde because it's CHO. So an alcohol doesn't react with 2,4-dinitrophenylhydrazine, but the aldehyde does. And on this compound, it's this nitrogen over here at the end, that's the one that reacts. And it reacts with the aldehyde that we have in our group. And it takes the two H's from there, and it takes the O, and that comes off as water. And it joins this double bond to that nitrogen over there. So if we have to redraw this, once they've bonded, our ring stays the same as it is. On that ring, the NO2 stays the same, and that NO2 stays the same. Then we've got our N, and it's still attached to the H, but then that other N that was attached to it joins to the rest of the compound. So that N becomes double bonded, where that double bond was, to the carbon, which still has its H on it, because only the O came off, and then the rest of the chain. So then from there was a CH2, a CH2, and an OH. So there's our resulting compound. And they say suggest the color of the organic product. So when we get 2,4-dinitrophenylhydrazine reacting with an aldehyde, we get an orange precipitate. Okay, so that's just an example of some of the kinds of questions that you might get in there. So if we look at one other example of a different way of showing it. So instead of a table now, they give you a flow diagram. And they say that that's a diagram which starts with a sequence of reactions from ethanol. So they gave you ethanol, and then they gave you different reactions to make different compounds with some of the information missing. And you need to know what we're adding to make things, or what gets made when we add certain things, and to be able to answer the questions from there. So the first question here says, draw the displayed formula of P. So displayed means, remember, we show all the bonds, and that's P over there. So that takes ethanol, and we react it with HCN and NaCN to make P. So I have an aldehyde, and I'm reacting with cyanide. So the cyanide ion, remember, breaks this double bond and it joins to that cyanide, and it makes the H join to the O, so we get a hydroxynitrile. So if I'm going to draw that out, starting with my carbon compound with just the H's, that's not going to react at all. So there's my first one. The next carbon where the aldehyde was, that's the one that's going to react. And I said I broke this double bond. And where the O was, I join it to an H. The H remains as it is. And the other bond where I broke that double bond from joins to the nitrile, which is the CN. So that means C is then attached to the N, and I know that a nitrile is carbon triple bonded to nitrogen. So there is my resulting compound of P. Then it says, name the type of chemical reaction that occurs in reaction 3. So now I've got to find reaction 3. So reaction 3 is going from an OH and a CO2H. So that's an alcohol and a carboxylic acid. And in reaction 3, I make a double bond. The carboxylic acid stays the same though. So I know it's only the alcohol reacting. And if it made a double bond, it means the alcohol came off. And it would have come off with one of the hydrogens from the other side, because there I only have CH2 and it was CH3. So the OH and the H came off, meaning it came off as water, and I made a double bond. So I eliminated the OH and the H to make the double bond. So I can say that this is an elimination reaction. Then it says, write an equation to represent reaction 4. And it says, use square brackets O to represent the oxidizing agent. So in reaction 4, I went from my OH and my carboxylic acid down, and I formed a double bonded O. From there, and the carboxylic acid stayed the same because that's as oxidized as it can get, as well as the CH3. So because I made double bonds, okay, I made a ketone from my OH. So I can draw out my starting compound of COH, H, CO2H, and then there was a CH3. Plus, it told me the oxidizing agent must be square bracket O. And that is then going to form my final product of my C with its double bonded O, CO2H, and CH3. Okay, and because I went from the OH and I double bonded it, I took away my hydrogens, so I can say that is plus H2O. So we always make water at the end if we're taking away any hydrogens, because they're going to bond to our oxidizing agent to make water. And then our last question says, state the reagents and conditions for reaction 4. So our reaction 4 going from the alcohol to our ketone being oxidized, we know that that oxidizing agent has to be potassium dichromate. So I can say K2Cr2O7, or I can write it out as potassium dichromate. And the conditions for that is that this compound has to be acidified. So we say that that is acidified potassium dichromate. And those are then our reagents and our conditions that we need. So if we look at the next following question that we have, it says that R can be used to make polymer W in 2 steps. And then they show you the 2 steps. that we have. And the first thing it says, draw one repeat unit of W's. W's at the end after we reacted it. So R says addition polymerization. So we added it to itself over and over again, made a polymer, then reacted it with sodium hydroxide. So if we look at what is R, so R is our compound where we have our double bond, but we also have a carboxylic acid group there. And we know that when we add a polymer to itself, you break the double bond and you keep adding it over and over again. So if we write that down, I've got the carbon. Where the double bond is, it breaks so that it can add to itself. I've got the hydrogen on each side. I'm going to add it to the next one on that side and the next one on that side. But over here, I've got the hydrogen, and then there's still a CO2H group there. So that would then be our addition polymer that we've made. So that's the intermediate over there. So that's what we've got. Now we took this and we reacted it with NaOH. So NaOH we know is a base, and the only thing over here that could react with it is this acid. Because remember, carboxylic acids react exactly the same way as regular acids. So over here, where I have this acid with the NaOH, I am going to take that H away, and it bonds with the sodium from there. So this then becomes my repeat unit, because I've got my C bonded to my C where I broke the double bonds, and the H's stay as they are, and then the carboxylic acid reacted with the sodium. So there is my final answer. In the next part, it says compound Z, and they gave you the structural formula of it, is produced from R. Z can be used in a two-step process to produce 2-aminopropane. In the first step, Z reacts with HBr to form two products, and the structure of the product depends on which intermediate is formed, intermediate 1 or intermediate 2. And explain why intermediate 1 is more likely to form than intermediate 2. So if we look at intermediate 1, the carbon ion that I have there is attached to an alkyl group there and an alkyl group there. Whereas intermediate 2 is attached to two hydrogens. So now when we form an ion like this carbon over here wants to get electrons because it wants to be whole, because it's a positive ion, so it needs electrons. So over here, the only place it's got to draw those from are the H's, and H's don't have many electrons to give. But here, it has carbon groups on both sides that could give the electrons to this carbon in the middle. So that's why we would form intermediate 1, because there are more alkyl groups around that could donate the electrons to that. So the more they are, the more stable it becomes. If this was also a CH3, it would be even more stable, because it would also then give to that. So when you want to explain a question like this, when they say, why do we form one more than the other? It's always going to be because of these groups, which we call alkyl groups, okay? Just like methyl, okay? From an alkane group, we say alkyl. So we say, due to this carbon cation having more alkyl groups that can donate electrons, becoming more stable. Then, when intermediate 1 forms, the product of the first step is T. Then it says, complete the diagram to show the mechanism for the conversion of Z to T and include all the relevant charges, partial charges, curly arrows, and lone pairs. So they have given us a double bonded compound reacted with HBr and it is then going to form a halogen alkane at the middle. So we're breaking this bond, adding our halogen compound with our intermediate in the middle to get our final in the end. So we know that when this compound, because remember this is electrophilic addition, gets close to the double bond, it pushes the electrons away towards our electronegative, so we can fill in our charges. The hydrogen is going to become positive, so we say delta plus. The bromine is going to become negative, so we say delta minus. And the bond is going to go from there, it's going to give its electrons from the double bond to the hydrogen. As it's breaking that double bond, it's going to take a hydrogen, and from there to the electronegative bromine. So we're going to draw a curly arrow from the double bond to the H, and from that bond to the bromine. That means that now I joined the H, but I was left without a bond, so that's why we have that positive. And this bromine took the electrons, so that means I'm going to end up with the bromine, and it took both electrons from that bond with a negative charge. And it's going to give those electrons to that carbon to get our final product of our halogen alkane in the end. So that's all we need to draw for our mechanism. And then our last question that we're going to look at says, T can then be converted to 2-aminopropane, and they show you the reaction. And the thing that they want to know is name the mechanism for this conversion. So I'm taking a halogen alkane with the halogen, and I swap the halogen for the amine group from the NH3 in methanol. So I go from that to that. So I substitute it because I'm swapping one for another. And we know that when we have our halogen alkanes, they undergo nucleophilic reactions. So our mechanism, we can say, is going to be nucleophilic substitution. Okay, so that's just some of the kinds of organic chemistry reactions that you might get to go through. But what you got to always remember is what you start with and what you're ending with, and you can see whether we're adding or substituting or what it's changing to sort of know what we're going to add or what we're going to take away for the type of reaction or for our reagents that we're going to use.